And when that happens, there's a latency of about 4 minutes before things come back on. So if I disappear, I'll be back in 4 minutes. I'm not vanished. I just need to warn you about that. It happens from time to time. So today I'm here to talk to you about what we are calling non-stationary tail risk beyond the present climate. Obviously, the conversation today is really about climate and sustainability. And I want to make three major points, which I'll, give these bottom lines up front. The first uh, bottom line is we're going to question whether digital twins are necessary and sufficient for us to manage complexity. And the second question is we're going to ask ourselves, how exactly are we going to handle non-stationarity? Is that going to be through data, through models, or a combination of both? How far ahead can we really look? And so that really begs the question, how much data and how much theory? And to put all this in this context, my presentation will kind of weave between the field and between theory. And it could be jarring, but hopefully I'll keep the transitions smooth. I've had the luxury of having some amazing people to work with, many of whom are listed here. And so today I just wanted to start with you
Hey,
to
Sai, I
take you to
think you may need to
Thailand.
share your screen still.
Huh?
I think you still need to share your screen. Sorry about that.
I did not share my screen.
I'm not
One more
seeing it
time.
yet.
Are you sharing my screen now?
Yes, thank you.
So that was so you can ignore my title slide. Uh, so I'm taking you now to Thailand. Thailand is, I'll take you to a few countries, journey out a few countries. And recently, if you've noticed, Thailand has been inundated with flooding. It experiences flash floods. They have interesting names for them. They call them rain bombs. Uh, They have tropical cyclones, very rare. But the one cyclone that does show up, a little category one storm coming out from Vietnam, way top, causes enough havoc that, for example, Vifa, the Nan province was completely inundated. Bangkok is barely meter or so above sea level, and it's extraordinarily vulnerable. In these countries, what you'll find is a kind of triple and quadruple whammy. The sea level rise causes salinization of the coastal aquifers because that groundwater is being depleted by industry. And once the saline water enters the groundwater aquifers, it's very hard to replenish them with fresh water. So the fresh water then floods the communities. And so the communities, A, don't have enough water during the drought season, and B, get flooded when it rains. These are the kinds of interactions that we worry about when we think about extremes, is the production of these complex events over short periods of time. It could be long too. And in particular, the interaction of salinity, sea level rise, storm tides, heat waves, and more landslides, for example, is a characteristic of some of the most vulnerable parts of our world, and Thailand is one of them. So how do people typically do this? Ryan did a great job of talking to us about risk. And the way we do think about risk is through the insurance world. Insurance is really good at understanding risk, and they've been at it for a very long time. And they think about risk as hazard, exposure, vulnerability. Hazard is what you know it. What's this, distribution of heavy winds, or what's the distribution of storm tides? Exposure is relatively easy. It could be how many assets are exposed. It could be what population is exposed. But it really is about what is your domain that's facing the hazards. And vulnerability is really its state of affairs. And the three of them, we like to think about them as the intersection or product or whatever it is, determine what we call risk. People use the word risk very interchangeably. Sometimes they'll say flood risk, and the x-axis will be, the depth of water, and the y-axis would be some notion of probability, which could be just the probability, it could be accumulated density, it could be the exceedance probability, or it could be the return period. Any number of things are used. And so it is this risk we are after, and it's not easy to determine. It's actually quite hard. And there are many, many loose bolts, and there are many, many difficulties in determining risk. But if we do determine risk, we then have to proceed to the next step, which is to determine impacts. What's the impact on agriculture? What's the impact on transportation? What's the impact on power? And then we design interventions. Should I build a levee? Should I build an embankment? Should I do something else? And we feed back this intervention into the risk estimation process, which involves simulations potentially, which involves other things potentially, and close the loop and see if this intervention has the potential to do anything at all. And eventually we converge and we say, that looks good. And we put it forward and say, all right, that's our approach to managing risk. So this is what we mean by risk-based resilience as being a foundation to how we become resilient as a society. And resilience is also being used in a very specific sense here, which I'll come to later. All right. On the right, you see a graph, which is really, I should have done a better job of it. The x-axis is the one going across, is some variable. Could be wind speed, could be water depth, could be heat stress, and the y-axis is the probability. And marching across time is to the northeast. And what's happening is the mean, presumably the mean is at the concentrated peak, that mean is drifting. This is what we think of when we say, oh, sea level rise, or the temperature is rising by 1.5 degrees or 2 degrees, or nowadays we don't ignore all of those. And we typically characterize the global climate in terms of the drift of the mean. But really what matters, as this talk will show, and perhaps others have, is what happens in the tails. There's a phenomenally more amount of energetic activity happening in the tails, but the mean seems relatively benign. And a lot of our climate conversations have been about the mean, but the experience of the extremes, the number of hot days, extreme rainfall, getting beyond 400 millimeters per hour, unheard of numbers. These tails, where are they coming from? Of course, those tails have an interaction with the mean. It's a very well studied, researched area, especially in oceans and climate, atmosphere and climate. Those interactions are determining this overall stochastic process that has a drift term about the mean and a diffusion term, which is about the spread of the tail. We need to manage sustainability as a process that is cognizant of both the drift and diffusion component, but rarely is this actually done. How might we do it? Here's an example in Thailand. This will take you 15 minutes on Google Earth Engine if you would like to do it. On the left is a picture of the flooding that was observed by satellites. That's rolling through the year. The year is in the bottom, you can see it. And on the right is a return period that's estimated from it. How many times does it flood? Once a year to once 15 plus years. Light shading means it's rare, dark shading means it's frequent. And you notice right in the middle, Bangkok is the most vulnerable, and all the rivers that flow into it. And we're going to stay with Thailand for just a little bit. And on the right is this is what we would mean by hazard. If somebody asked you for a hazard map, typically they'll go to historical data and they'll produce this hazard map and they'll say, that's the hazard Thailand is facing. And when we want an exposure map, it's a bit more complicated, but we've got some very good tools nowadays. For example, this is the nighttime light activity as it's been changing over the years. And let me play that again. You might have, if I could easily do it, I would do it, but loop, there we go. So if you look at this, you see that the nighttime light activity has been growing about the same period of time. And this is the delta from 2013 or so. And a lot of people have done this work as to try to determine exposure by nighttime activity, because obviously it determines population centers. What you should be noticing when you look at this graph on the right is that the population is growing precisely where the hazard is. You would say that's the dumbest thing to do. Why would you want to settle where the hazard is? This is because people live along rivers. They live where water is. They need the water. And so It's a very complex interaction just between hazard and exposure, understanding what's happening in present climate. And beyond that, we might want to ask, how do we map vulnerabilities? Can you imagine going to the city of Bangkok and asking for a vulnerability map of every asset there is? I mean, you're talking about bridges, roads, pipes, subterranean structures, transportation systems, electrical power grid. The city probably doesn't even have enough data to do it, let alone being able to provide you in a reasonable way. And the whole, like Bangkok, many, many cities around the world. Take your pick. New York, East Boston, Florida, many, many cities, and others around the world are all excited about mapping their vulnerabilities without probably realizing how dangerous this is or how difficult this is. So we've been asking this question, how can we get a glimpse of the vulnerability? Where is this information embedded? When we talk about complexity, we always compete between two very different poles. On the one hand is the detailed representation of the interactions between the elements that constitute the system from where complexity emerges. And on the other hand is to simplify that representation enough to reveal the essence of the complexity. Ed Lorenz was very good at this, where he would build simple models of very complex systems. But it is in that simplification, or it is in that simplicity uh, without it is in that simplicity, I would say, that the answer lies. To reduce no more that it becomes trivial. And so we've been asking ourselves, where does this information about vulnerability live? And we found that it lives in conversations people have. It lives in music. It lives in old stories. It lives in newspapers. It lives in books. And so what we did was, we did the only thing that anybody would do. We stuck a RAG LLM in there. And we mined, and we've done this in many, many cities. We mined all the old available information in the form of print, in the form of news that we could digitize. And we built a knowledge graph. This knowledge graph runs upon a vocabulary that is a damaged vocabulary. It is terms that we seed and those terms grow, and it's a RAG-based model that's coupled to this LLM. And quickly, I would say within few hours, as opposed to few decades, we are able to ask and answer questions like, what is the most vulnerable part of Bangkok? What are the top 5, or which ones are most vulnerable? It tells you how many, the number, it sets the number itself. Here, for example, shown in red are actually the most known vulnerable parts of Bangkok. I'll show you an animation. And in this animation, you'll see that as we go through these areas, it gives you the reasons for why they're vulnerable. It has mined this, and it gives you a trace to exactly what news article or what sources of information produced this vulnerability assessment. So we call this push forward. It's ordinary vulnerability assessment that tells you, tell me what the most vulnerable regions are. If I wanted to protect them from flood, where should I focus? And for us to get to this level of understanding for Bangkok would have taken years, decades. Some would be easy. You might have to just look at a digital elevation map, and that might be enough. Coastal DEM would probably do a great job. But to understand really where these interactions are, what these vulnerabilities are, and what the causes could be, because this lives in a subspace of a very, very high dimensional space. But these interactions don't live in that high dimensional space. They're much lower. And that's what we tap using this knowledge graph structure. I don't have the time to go into the details of it, but I'm very happy to talk about that separately if there is interest. But we can also do other things with this kind of mapping, which we call causal traces, going backward in time. Here's Bangkok Airport, Suvarnabhumi Airport. And we asked the question, what are critical components that are connected to it? It turns out there is this one substation, 115 kilovolts. You wouldn't notice it. And its pumps, that substation tends to fail. And when it fails, the pumps in the airport stop and the airport floods. 70% of national air freight stops. Sort of assessment. And the pumps fail, the water goes beyond 0.6 meters, which is really not a lot. That's like a joke flooding. So when you think about this, and then you can assess how much damages there are, creating these network structures, there are just understanding these interactions, looking for correlated damages and losses, and answering questions. If this were to be damaged, what would be the cause? And if I were to experience really high damages, why would that be? Thinking about vulnerability assessment as an interactive knowledge engine has been giving us some benefits. Okay, I'm switching now to a different country, Bangladesh, Southwest Bangladesh, in fact. This very corner here. Bangladesh is a very interesting country. If you've never been there, I urge you to go. Some of the most friendliest people in the world. But it's screwed. The whole country is screwed. I'm sorry to put it that way. Out in the bottom, the color here you see are basically watersheds. And out here in the left on the map, you see are the Sundarbans in green. And what happens is, again, same story. Sea level is rising, cyclones come, rainfall falls. And what Bangladesh did was very, very interesting, actually. It built these things called polders. It's a Dutch word. Many of you probably know it. These are these white closed contours. They enclose a community within. So presumably to keep them safe. And then in the middle, you see a typical polar embankment. Unfortunately, what's happening is, again, a triple or quadruple whammy. Firstly, because of these polders, when the tides come up the channels, this is a coastal delta, very low lying. If you had sea level rise of 2 meters, probably a third of Bangladesh is toast, so to speak. I'm putting it in stark terms because it is stark. And if you look here, this water that comes up from the ocean, from tides, there could be storm tides, there could be action of sea level rise with storm tides, there could be just tides, high tides. This water comes in, but instead of flooding the land, it rides the channels and canals and goes much further up. This tidal amplification is largely because of these polders. India, up to the northwest, has been damming all the rivers, and they reduced the freshwater fluxes. So the seawater is finding it freer to go further up, bringing much more saline water. Moreover, the land inside the polder is subsiding. The land outside where the river is rising because of silting. This means when it rains and it waterlogs, they can't pump the water out. Moreover, because the soil is now salinizing rapidly because of the salt water coming in, people have started putting these kind of pumps to bring salt water into the polder so they could do shrimp farm. It's a right royal mess. And so there's again the story of drift of the mean, which is this salinization with the extremes. One cyclone, pardon me, one cyclone is all it would take to make the whole soil saline. And up to 8 years after that, you will not be able to grow rice. Excuse me, just 1 second. Okay, can you still see my screen, Ryan?
Yes, we can. Bless you, by the way.
All right. So what have we been doing in Bangladesh? We've been talking to people and helping them play games to solve decision problems. And the decision problems that they're solving are really about figuring out how is it they're supposed to manage their communities at the local scale, folder by folder. And so they need to build structures that will enable decision-making processes. So I'll give you a bit of an example. Here you see two examples on the left. The community, literally, you can join me on the browser and play this game with me. We can add nodes. A whole bunch of people can play across the world. And these graphs are created between hazard nodes, nodes where they have, for example, occupations, intervention nodes, building agrivoltaic systems, and internal state nodes like waterlogging. And we drive this simulation using our projections, which I'm going to talk to you about. And sorry, we drive them using our projections. And then the graph does belief propagation of various kinds. Some of these are process oriented, some of these are statistical. And eventually they get impact assessments on their farmings. After that, they play a game. So here you see the game in progress that's being played. And people can invest in various portfolios. They could be doing agriculture, they could be doing aquaculture, they could be growing shrimp, they could be going to Sundarbans and extracting honey. It could be a businessman, a day laborer, a migrant laborer, and so on. And they play this game, and if they have enough money, because we monetize all actions, if they end up with enough money, then they found a sustainable outcome for their community over a number of hazards that have been impacting them. For example, here you will see on the top different events being generated, everything from community events to extreme hazards get generated, and their resilience game that they have to play is to end up with enough money in the bank so that they can declare themselves to have survived these oncoming threats, which are produced through simulation in a changing climate. So this is what we've been doing in Bangladesh. And the hazards that we think about are wind, storm tides, rain, inundation due to rain, but also salinization. This animation that you see on the right is a sensor network we've deployed to measure soil salinity. And it's one of the lowest cost sensor networks on the planet. It probably costs $400 a year to run. And it's designed by it's operated by the community. They go and take measurements, and they take measurements when the system asks them to, as it tries to reduce uncertainty or reduce bias. On the right, you see red is salinity that is greater than 3 decisiemens per meter or millisiemens per centimeter. And you see that the southwestern part of Bangladesh is salinizing. And this is all extracted from Landsat. And now more recently, we are using Sentinel as well. And we build models for how the surface reflectance properties of soil salinity are modified using machine learning algorithms. But what we are noticing is the dramatic salinization of Southwest Bangladesh over the last 10 years. And we think that in the next few years, all of this area, home to over almost 1 million people, I would say, this entire area, will not be able to grow rice. And they'll have to find something else. So when we talk about a sustainability stack, we are thinking about the hazard, we're thinking about the exposure, we're thinking about vulnerability, and I've shown you different aspects of this. And we're thinking about impacts through these graphs. And these graphs aren't built through some big, guy from the West coming in and saying, I know what to tell you. They're mostly built by people understanding their land, understanding how it has been. Of course, science is involved, but they build these graphs and they're solving specific problems as a result of it. I would like to solve my waterlogging problem. How do I do it? We build the impact assessment, we do the simulations, we play the game, and What does the investment portfolio look like? Should it involve managed aquifer recharge? Should it involve some other process? Should we couple it with agrivoltaic? What should we do? Often this type of process helps communities transition from fatalistic near-term thinking, what's going to happen to me next season, to risk-based thinking. What would happen if the frequency of cyclones were to change? That's the first thing, because when you play a game, it's the roll of a die, it's a chance, and risk is immediate. The other thing it does is it democratizes the process. Everybody plays the game. The third thing it does is it loosens people up. They're not as the game is a game. If you lose, you go back home, you start all over again. It's no problem. But once a solution is revealed, it becomes immediately enticing. And in fact, we have one community in Nonstationary where that is actually true right now, and we're implementing an outcome. It also reveals gaps. Managed aquifer recharge takes a lot of money. And should we bring an NGO? Should we bring a bank? Those become players. So the game structure scales. So we've been looking at mixed initiative serious games using knowledge graphs, again, built in conjunction with humans as well as and simulating those knowledge graphs using our climate projections. And I haven't told you anything about that yet, but about our climate projections for the extremes, not the mean in most cases, because the extremes is where they've been facing this impact. And we've been looking at salinity, we've been looking at cyclones, we've been looking at rainfall, we've been looking at a number of variables, heat stress. In doing so around the world, Bangladesh and Thailand are the two places where we've done a lot of work, but we've also been looking in the US, in East Boston and Logan Airport. How many of you know Logan? That's another one of those disaster zones waiting to happen. I'll tell you all about it towards the end of my talk. All right, now let's go to the next point, which I want to make. So I hope I've characterized what we mean by risk and resilience and how we are thinking about the sustainability stack. The stack at the bottom containing these games people are playing with the computer. And by the way, one of those players in my game is a reinforcement learning algorithm. It sucks. The people actually are quite good at playing the game. In a few iterations, they find the right strategy. The reinforcement learning algorithm bangs it against the wall many, many, many times, but eventually comes up with a really good policy. So humans still have a bit of an edge. Thank you. Is what I'd like to say. But above that, game process is the impact process. Above that is the vulnerability process. Above that is the exposure process. Above that is the hazard process. And I've already potentially convinced you of the role AI has played in most of these processes: exposure, remote sensing, vulnerability, large language models, impact assessments, belief propagation on potentially causal graphs, but could be probabilistic acausal graphs. And the fact that this decision making can happen at all scales make this very, very interesting. But you should be asking the question, how do you know what the vulnerability is going to be 50 years from now? How do you know what the exposure is going to be 50 years from now? How does all this translate to climate? If all you did was look at your feet while you're walking, you'll probably stumble a lot. But if you were to be able to look ahead and see what's coming, your path could be much, much, much better. So if we could forecast, or if we could project what the impacts of climate are meaningfully, potentially we could come up with much better strategies rather than constantly react to climate change. People react anyway. But what is this part? What are we going to do about the oncoming climate change? Where are we at? Of course, all of you potentially seen these graphs about various pathways and IPCC 6 scenarios with the multi-CMIP model and the great fan that gets produced under various scenarios. Even if we were to pick a scenario, for example, if you were to pick SSP 370 and say that's a good one, we really are relying on a model or an ensemble of models that are imperfect, have model error, and that scenario may not play out. So there's a whole bunch of uncertainties regarding the scenario, regarding the model, and even regarding the physics and the parameters and the parameterizations that play into this story that need to be considered. So when we're talking about future projections, we really have to thinking about uncertainty. What about doing it using data? We say, who cares about all these models? Why not just look at the past observations and build a model and put it in a STM at the end of it? or to become more sophisticated, maybe build a neural operator. And there's so much machine learning happening now. Aurora has just come out. And what's the big deal? Just train it and you'll be done. To use ERA5 analysis, train it and run it. The problem is that this is difficult at the extremes. Let me tell you the story of Bangladesh. You have 30-odd cyclones in Bangladesh, and shown here in blue dots. The x-axis is the wind speed, the y-axis is the return period. Okay, for 30-odd storms over 30 years of observations, let's say, what would be the return period you would estimate for the most damaging or the highest wind speed storm at 140 knots? Would you say it's 30 years? Or would you say, I don't know? I mean, what if that storm doesn't show up for another 100 years? What is that uncertainty? In fact, if you use rank-based statistics, you can easily estimate the uncertainty that is associated with it, and it's almost 3 orders of magnitude. It could have a return period anywhere from 30 years to 1,000 years down to, it can go down. So the first problem is risk is not easily determined by few observations. It's very difficult, in fact, which means that even in present climate, if you wanted to know what the tails are, you have to do something more than just tell me that you've seen cyclones. It's for ordinary weather, like daily temperatures, temperature means, it's probably okay. But for the tails, it's not. And so the problem we have is how do we model these rare extremes using observations when, first of all, there are no observations in the future, and B, there may be very few observations up to present time. And so even in present climate, we have a problem, let alone all the uncertainty that the climate models tend to produce themselves or the climate scenarios present them, and so on and so forth. So I'm going to try to present this picture to you about how we think about the sustainability stack, and what I'll then go around the cycle and point out to a few key pieces of work we've done. Hopefully all the dots connect for you. What we would ideally like to do is like the soil salinity map that we had provided using satellites or remote sensing, very measuring it through present time, very laboriously, very intricately. We would like to project it to the future, but we can only go to a very short range into the future. We don't have the data-driven skill to go much further out. How are you going to predict what the salinity is going to be 30 years from now? Soil salinity, very difficult problem. But if you had a numerical model and you could do tides repeatedly, you could do groundwater modeling, you could in principle, if you built a digital twin of the earth, you could in principle do it. And at the beginning of my talk, I said, we should probably not be thinking about digital twins. So I'll tell you what the alternative might be. So because this is difficult to do, what people typically do is they take everyday observations and they assimilate them into high resolution numerical models. This could be really rather high, kilometer scale models, explicitly resolving convection, for example. And the problem is even simulating these forward in time is very expensive. You could probably do a calculation and see if there's enough energy on the planet to try every parameter perturbation under every scenario and deliver a large ensemble. You could probably arbitrarily create a case or a set of parameters where you would say not enough power, not enough energy available. So high resolution simulations are expensive and they're difficult, and computational magic keeps happening, but it remains a problem. And here we are making some advances in machine learning, right? For example, you can look at ECRT2, CoreDiff engine. You could look at particularly models that seem to be running coarsely, but do some internal downscaling. Or there are other models that natively run at very high resolution. I would like you to be a bit alert to the fact that these models aren't particularly necessarily applicable to future climate. They're very good for forecasting, but it's not obvious that they'll be useful in climate. That might change, but not yet. So the tradition has been to reduce the model, We call these climate models, and reduction is often very simple. It's filtering the equations or the grid and parameterizing all the subgrid scale effects, for example, parameterizing convection, or other parameterizations of turbulence. And then we launch our forecasts, as in just a dumb ensemble, way out in the future, 30 years, 100 years, and that ensemble determines uncertainty. Sometimes these climate models too are just run one a piece, and so between all the models, we would say that they somehow capture the spread of model error. That's a bit tongue-in-cheek because each of these models have their own biases. And the fact that they generally agree in present climate, but they don't in future climate tells you that there might be an overfitting problem somewhere. So there's a lot to be teased out there, but that's what we have. Now we have to reconstruct all the hazards. And here, very important for us to solve a downscaling problem, which is the production of fine resolution that at the scales where the sustainability decisions are made. And that downscaling process has turned out to be very, very critical. Following which, we do exposure, vulnerability, impact, quantify risk, and then solve the decision cycle, take an action today and close the loop. If you're a controls guy, you would say, wow, that looks like model predictive control. It is. Predict forward, correct backward. It looks like a 2-point boundary value problem. Go out forward, you have a sustainable goal, take that error signal, bring it back, do some adaptation. So it is quite a bit of an example of projecting forward and back projecting decisions. And you could think about this in terms of reinforcement learning. You could think about this in terms of stochastic dynamic programming. Any number of frameworks are available to implement this sustainability stack with some caveats. We are able to project the hazards forward, but we're not able to project exposure, vulnerability, and impact forward today. This might change, but not quite. But even that conditional difference, that conditional delta, okay, everything else is held constant to today, but what happens if the temperature goes up? What happens if we can simulate new extremes? What is the response of the system is still meaningful. And even if the calibration is a problem, like how do you know the climate model is doing well in present climate? And you kind of force it to match the statistics of what you observe. People do crazy things, but even that, by looking at the difference in the signal between the climate signal and present signal is not so bad. It gives you, even a bad thermometer could be useful if it's consistent. So there are a lot of issues with this, but we don't really have many tools. And there's a lot of open research questions. But I would say that if this cycle were to be really well implemented, we should be in good shape. And it will change over time, but this is what we think of, my group and my work. And we work across all of these topics. In all of these topics, we have physics, we have AI, and we are constantly struggling with how much of what goes into each to be able to solve that particular bullet or that particular box. So with that said, I'm going to give you 3 examples. We may not have enough time, so I will run through a little bit faster. And I'll give you 3 examples of how we solve this critical problem. I'm not going to focus on the decision games, which I've already discussed. I'm not going to focus on exposure or vulnerability, or which I've kind of described. I'm going to focus now on downscaling. What we mean by downscaling is that the model, which was lifted to a much coarser resolution in enabling these long-term projections. Of course, you would say that why do you need all that resolution when you're doing a climate simulation? I mean, climate's a boundary value problem. What do you care about all these initial conditions for? But when you get to that time scale, when you get to that future, that intended future, 2050, 2060, you need to recreate all the structures that impact weather at that time, because that's where the extremes are to be found. And so we do need to worry about downscaling. So one of the areas where we've done a lot of work in downscaling is on tropical cyclones. This is one of probably the most beautiful downscaling pieces of work I've been a part of. And this was actually done by Kerry Emanuel, because he came up with this theory, very simple theory, of a cyclone as a Carnot engine. And I'll talk about that in a moment. So it's purely physics based. And here's the, very time somebody says physics, you think, oh, that's a huge computer model with lots of resolution, dot, 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 breaks the bank. No, it's quite the opposite. And this is a very MIT way of thinking about it from the Lorenz School. We're all part of the Lorenz School, where we use the physics, but we use it and simplify it in a way that the essence of the nonlinearity is revealed without burdening us with the computation. Can we do it? Requires a lot of ingenuity. And importantly, in present day, we can use machine learning to discover these low-dimensional dynamical systems. That could be very, very interesting. If we get time, I'll talk about how we are doing that to discover equations that would help describe not tropical cyclones, but extratropical cyclones, which are much harder. So this is a physics-based approach to downscaling. It does not rely on the observed hurricane record at all. And it is applicable, therefore, where nature has not produced storms, has produced too few storms, or none at all. Just because a certain part of the world hasn't seen a cyclone doesn't mean there's no risk. And so we can help resolve that. And it's the only such known method. There's a lot of new methods still coming in across that are data-driven, but this is the only such known method that uses purely physics. And it embeds basically a 1D coupled ocean atmosphere model inside a climate model. So it's like a simple 1D process that's running along tracks that are stochastically simulated. And as it runs along the tracks, it produces all the intensity structure that we need, or the storm structure that we need. And it basically does this because it frames the equations that are needed in angular momentum coordinates. So it doesn't rely on having a grid cell of a certain size. It can, in fact, resolve the cyclone intensity infinitely, just in angular momentum coordinates. So that's why this turned out to be quite useful. And it's been used, the CHIPS system has been used to forecast cyclones. JTWC has used it. I don't know how many else have used it, but I know that JTWC have used it. And there have been literally, since we started this work in 2005, when our first paper came out in BAMS in 2006, and we started a company, and we did the first storm surge simulation using this method. And when we looked at the distribution of the statistics of cyclones we produce, they match really well where nature has produced good cyclones, number of cyclones, without ever relying on any of the observed history. And it's a really simple. The business model, Carrie Emanuel and I have our 2 laptops. And we've done okay. So this is one example of how physics has been used to help resolve risk. And I would not go into more details of this in the interest of time.
Yeah, Sai, just a quick note. We got about 6 minutes left in the seminar, but just wanted if you wanted to take some questions, just to be conscious of that. Thank you.
I'll stop in a moment. And so here are examples of how we determine return periods, both for wind and rain. And we've been used this to study storm tides in Bangladesh. Here's synthetically simulated cyclones on the top left. Here's a simulation. This is actually for a known cyclone. So we're showing you our model for, and with storm tides. It verifies very well with the observed cyclones. Our approach incorporates projections of sea level rise. And we produce the first characterization of storm tide, coastal storm risk in Bangladesh. This paper got a lot of attention because it basically argued that there's a 10-fold rise in risk. No matter which scenario you look at, there's a 10-fold rise in risk. And we've noticed that there's a mingling of the late monsoon season and the cyclone season. So monsoon and cyclone seem to be coming together. The heat stress season and cyclones also seem to be overlapping, but we haven't seen as much evidence. The late monsoon season, in almost all scenarios, we've seen that there's an increased activity or severity of cyclones in the late monsoon season, which is potentially extraordinarily dangerous. We've looked at attribution of historical storms and how much more, in how much more frequent they would be. But now I want to just come up with 2 points and then I shall stop. When we talk about flooding, it's not just cyclones. So obviously, here's an animation of a cyclone coming up the coastal Bangladesh, and you can see the water coming up inland, generating an overland flow. Of course, it's riding the channels, but we mask them. You can also have rainfall-driven processes. You can see all the rainfall producing inland inundation. And really, we think about compound flooding as being a coupling of those two. But it's not just compound flooding. It's cascade risk too. You get a cyclone event and you get a monsoon event, especially with this overlap. The soil contains memory. How do we deal with this cascade risk is now become very important rather than thinking about them as independent IID distributions. And so this type of downscaling, which I will only show this one slide and then I will stop, is also of interest, and this is more traditional. On the left, you see rainfall over Bangladesh that is being simulated perhaps by ERA5 or some climate model, I don't remember. On the right is an equivalent picture that CHIRPS would have produced, the satellite. And this downscaling of rainfall is important to drive flooding because precisely of the graph on the right. If you look at the blue graph, this is what ERA5, which is a reanalysis model, produces for extreme rainfall. These are 90th percentile events or over. And all the plus signs are the events that were detected. But if you look at CHIRPS, the satellite, which is a 5-kilometer resolution, and ERA is a 25-kilometer resolution, you see that it has a huge difference from 100 to 200 millimeters per hour. So either ERA is way on the left in terms of the return period, or there's a systematic bias. And so we've come up with a downscaling method that uses just a little physics. We have a notion of what this spectral structure of the precipitation field should be using, for example, orography. Just a bit of statistics from past observed storms so that the models that we build are very well conditioned. And machine learning, which is using a GAN to train it to do the downscaling. This little triplet, a little physics, a little GAN, a little ML, and I guess it's a lot of ML, but a little physics and a little statistics and ML together provide us with downscaling functions that appear to be invariant under climate. We still haven't gotten the entire story behind that. So we train it in present climate using ERA as the input and the satellite as the output. Notice that these are two different modalities altogether. We somehow train it, and then we apply that downscaling function in future climate. So we are able to generate these tails that drive the flooding. In this case too, we don't have a numerical physical downscaling. We have a statistical downscaling approach that uses enough physics to make the problem tractable at large scale. I think I shall stop there because we're out of time, but hopefully this conversation has been interesting. And if you have any questions, I'll take them.
Thank you so much, Sai. People are clapping online here. So I think we have maybe a minute or two for a couple of questions. What I'm doing with these seminars is there's more questions than we have time in these 1 hour meetings. So I'm archiving these on Slack, and people are picking up the conversations there. But I want to maybe ask Regina's question, or invite Regina to voice her question that was put into the chat about the Thailand example with the knowledge graph. So Regina, go ahead if you're able.
Yeah, thanks so much. This is super, super fascinating. I was wondering about the knowledge graph in particular, and if it's able to discover things that haven't happened yet, or is it basically just limited to things that have already happened, vulnerability-wise?
So we've asked it what ifs, which are not explicitly part of the. So what is a knowledge graph? A knowledge graph is a graph between entities, captures relationships between entities. And what are entities? They are any and every term that we associated with the vocabulary that knowledge is about. It could be damage-related variables, it could be structural variables. How do we identify these variables? We seed them. Initially, we tell them, here's your seed. And then it uses those to add more terms. And it constructs a knowledge graph. There is some curation involved in it, but once that graph is drawn, there are certain types of questions it can answer, which is something you may not have thought of, but emerges purely by following the graph structure and looking at what shows up. It can also reduce if it goes from variable A to B to C and it needs to do transitive closure, it does it. And it says, I don't need to tell you all these things in the middle. This is what's going to happen to you. So all of that is true. But does it discover new forms of causal structures? The jury's a bit out. I'm not quite sure that it does, but it has, whenever we've asked it a question, and I'll invite you to play with whenever it's asked it a question, it has surprised us with how good that explanation is. Because with these graphs, whole purpose is to generate explanations. And so vulnerability is no longer about producing a spatial map, but it's about playing with a domain and asking questions of it. So it's an investigative process. And if you're an insurance company and you wanted to insure some part of Thailand, you could tap a question and say, okay, what are the most vulnerable hotspots connected to this property? If this property were to lose 10 times what it normally loses every year, why would that be? These questions can be answered, but they're a different way of looking at vulnerability than the usual way. So I would say partly, sorry, long answer, but partly we're not sure, but we think so.
That's super cool. Thank you so much. That was very clarifying, the response. So thank you.
Yeah, thank you, Sai. If you have a link for how we can explore that or just read more about it, we'd love to take a look at that. You can send it to me and I'll post it. I think we're a couple minutes over here. Thanks so much for hanging on, everyone. Sai, thanks for joining us late at night there. Thanks for such a stimulating talk, and we will follow up with resources. This has been brilliant. Thank you so much.
Thank you so much for having me. Bye-bye.
Bye-bye, everyone. We'll talk to you in a couple weeks.